Hello everyone, this is Dr. Lennon, and we're going to go over Module 1, Part 2 today, so we're going to continue with the second half of this homework. We're picking up with scientific notation, so the main thing with scientific notation, converting to regular notation, is if the exponent is positive, you move that many decimal places to the right, and if it's negative, you would move that many decimal places to the left. So negative 6.47 times 10 to the fourth here, we would move that decimal 4 places to the right. So we'd move past the 4 and the 7, and then we'd have to add 2 zeros, and that's where the decimal would go. So we have negative 64,700, and that would be the answer here. For number 34, we have one finally where we're moving to the left. We have a negative exponent, so 6.3 times 10 to the negative first. We just move one place left, so that would make it 0.63. Okay, again, write the number in decimal notation without the use of exponents. We're just moving the decimal 7 places to the right. This is going to be pretty similar to the ones we've seen so far, so nothing different there. Number 36 is a bit different just because we're going the other way. We have a number in standard notation that we want to put in scientific notation. So basically that means you just need to move it so that it's a number between 1 and 10. There's quite a number of zeros here, so you really got to keep track. Let's count how many zeros between the decimal place and the 5. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 of them. 4, 5, 6, 7, 8. And then we've got 5, 6, 3. So this decimal has to move past 8 zeros and then the 5. So that means it's going to be negative 5.63. And we moved it past 8 zeros and 1 5, so we moved it 9 spots. And notice this is a very, very small number, which means it's going to have to be a negative exponent. Multiplying by 10 to a negative exponent is going to make things smaller. 10 to a positive exponent is going to make things bigger. So you really just have to pay attention to counting there. Counting the number of zeros is the hardest part. But really it should be straightforward. And again, when you're doing scientific notation, the number in front, in this case the negative 5.63, the absolute value of that number always has to be 1 and 10. So I couldn't have put the decimal point between like 6 and 3, let's say, because that would be 56.3, which is too big. So let's see if we counted correctly here. And we certainly did. Okay, so when we're multiplying these things, when we're doing these operations, it's similar to when we were doing the exponent operations with the algebraic expressions. So we want to group the tens together and group the regular numbers together. Some calculators will actually have a scientific mode where you can just use the scientific mode, and it will always write the numbers in that form, but we can do it by hand as well. So again, we're going to regroup these. So instead, I multiply by 1.7 and my 2.2, and then I multiply my 10 to the 17th and my 10 to the negative 10th. And the nice thing about multiplying the tens together is we can just add their exponent because they have the same base. So 1.7 times 2.2, right, we just want to punch that into a calculator. If I weren't lazy, I could just do mental math. It's 3.74. And then when we add the exponents, 17 plus negative 10 is 7. So we get times 10 to the 7th. And that is our answer. So 3.74 times 10 to the 7th. Okay, so we have another one. This one is division. Again, remember with the tens, that just means we subtract their exponents. So number 38 here we have 1.9 times 10 to the negative 4th divided by 9.5 times 10 to the negative 10th. So if you do 1.9 divided by 9.5, you get 0.2. And then when you subtract the exponents, remember this is 10 to the negative fourth minus negative 10. It's the top exponent minus the bottom one. So we have 0.2 times 10 to the positive sixth. Now the only issue here is 0.2 is not between 1 and 10. So we need to actually rewrite that. So notice, if we took away one of the 10s, we could write this as, say, 2 times 10 times 10 to the fifth. 0.2 times 10 times 10 to the fifth. And that 0.2 times 10 will turn into 2. Right? Sorry, I'm getting a little bit sloppy here. So the 0.2 times the 10, this becomes 2. So this is really the same as 2 times 10 to the fifth. And that's the form we want to use because scientific notation requires that the number in front be between 1 and 10. So this is going to be 2 times 10 to the fifth. So there's that one extra step. You may want to quit at 0.2 times 10 to the sixth, which is equal to the correct answer, just not in exactly the right form. Okay, so we're looking at some square roots here. Again, getting into the radicals. The definition of the square root is pretty straightforward. The square root of, say, a number k is the number x such that x squared is equal to k. Technically, it's the positive number x. The principal square root is always going to be positive. If you would put a negative in front, that would stand for the other number, right? Because in this case, if we're looking at, say, the square root of 49, there are two numbers that you can square that would make 49, 7 or negative 7. But if you just have the square root of 49, it's only indicating the positive solution, hence the principal square root. So this would evaluate to 7 because if you do 7 squared, you get 49. So it's like squaring a number in reverse. Again, this function is available on all calculators, but it's good to do it mentally. In this one, we have a negative in front, so we're going to get the negative solution. Again, you just want to practice your, think of your numbers that you know that square to things. So if you have negative square root of 121, well, the regular square root of 121 is 11, and then we just keep that negative in front. So this is going to be negative 11, again, because 11 squared equals 121. Oh, I forgot the negative. Whoops. Forgot to type that negative. Okay, this one is to indicate kind of the issue with order of operations. So square roots by their nature are related to exponents, which are multiplicative in nature, not additive or subtractive. So if you look at something here where you have the square root of 25 minus 16, we have to use the order of operations, which means what's underneath the square root we need to perform first. So this should be equal to the square root of 9. Which we know is going to be 3. Note that the square root of 25 minus 16 is not equal to the square root of 25 minus the square root of 16, which would be 5 minus 4, which would come out to 1. So that's a common mistake you'll see many students make, but you want to do the 25 minus 16 first, and in that case we get 3. So it's kind of a warning there. This one, on the other hand, the subtraction is not performed beneath a single radical. So you would simplify both of those square roots first, and then only from there move on to doing the subtraction. So the square root of 256 minus the square root of 144. Well, this is 16 minus 12, which is just equal to 4. Okay. Now, for some of these, when they don't evaluate perfectly, essentially, the square root will undo the square of a number. So that's kind of something we're looking for. So here's kind of like a property. let's say if k is greater than 0, then greater than or equal to 0, we can say, then the square root of k squared is just equal to k. Essentially, our square root will cancel with any perfect square. That's what we're learning. But 250, it's not so clear. That's not really a clear square. So what you want to do is break it down into its prime factors. So if we're trying to do the square root of 250, first determine, let's say, the prime factorization. Or we can determine any perfect square we see in that. Let's say a perfect square factor. That means something that you know is a perfect square that divides into it. So we know that 25 is 5 times 5. And it's pretty clear that 250 is 25 times 10. So we could rewrite the square root of 250 as the square root of 25 times 10. And then this can actually be written as the square root of 25 times the square root of 10. This property will work with multiplication, even though it didn't work with addition or subtraction. So this would then simplify to 5 square root of 10. So this is kind of another thing that we know, a proposition. So we know that the square root of, say, capital A times capital B can be split up as the square root of A times the square root of B. And similarly, the square root of A divided by B is the same as the square root of A over the square root of B. However, those same properties do not hold for addition and subtraction. So we use that in the second step here to simplify the square root of 250. So we would write this as 5, and then there's the square root button down here, 10. Okay. We're going to do the same thing here. Again, we have some x's involved, but we know that square roots cancel out with squares, so we can just treat the letters as if they were regular numbers. So number 44, we have this square root of 242 x squared. So we'd like to know, do we see a perfect square factor of 242? I'm trying to think. Half of it would be 121, and we know 121 is 11 squared. So maybe it's easiest to think of this as the square root of 121 times 2 times x squared, and then we know we can split all three of those up. So we can do the square root of 121, we can do the square root of x squared, and we can do the square root of 2. And I'm just writing the square root of 2 last because that's the only one that is not a perfect square, right? 121 is 11 times 11, and x squared is x times x. So we get some cancellation. So we end up with an 11x in front, and then the square root of 2. So that would be our answer. Oh. It's possible that x is negative here. So technically the square root of x squared, this is a complicated bit, and I think it only happens on this one problem. But yeah, they didn't specify that x was positive, so it's technically 11 times the absolute value of x times the square root of 2. Because the square root of x squared can only be a positive number. You can't have the principal square root of something be negative. So we need to add some absolute value bars in here. This should be the only question on this homework with this problem. Yeah. Like on this one, you'll already notice that it says assume variables represent non-negative numbers. So we already know x is not necessarily negative. So for that reason, we don't need to include absolute value bars. But okay. So for number 45 here, we've got the square root of 3x times the square root of 81x. So I can put those together and multiply all under one thing, but I'm going to leave the 3 and the 81 apart because I already know 81 is 9 times 9, so that's already a perfect square. So I'm going to rewrite this as 3 times 81, and then your x times x makes x squared. And the whole reason for that is I know that the square root of 3 is already simplified. It's a prime, so it can't be simplified any further. But the square root of 81 is going to be 9, and the square root of x squared is just going to be x. So I end up with a 9, an x, and then a square root of 3. Again, we don't need the absolute value on this time. You just needed it on that one problem, 44. A little bit difficult to notice. Okay, so we've got the square root of x to the 9th now. So when you have something like this, basically square roots are going to simplify as long as they're dealing with an even exponent. So if we have the square root of x to the 9th as such, what I can do is I can actually write this as the square root of x times x to the 8th. Right? Because remember, when you take from the rules of exponents, if you multiply two factors with the same base, you just add their exponents. So 1 plus 8 makes 9, so I know both of these are going to be equivalent. And then I can split it up as the square root of x times the square root of x to the 8th. And I know the square root of x to the 8th is actually just going to be x to the 4th. So I'm going to end up with the square root of x to the 4th, or x to the 4th times the square root of x. And that's because, remember, x to the 4th, if you squared it, you would get x to the 8th. Right? You would multiply the exponents in that instance, and that's essentially what's doing. So if you have the square root of some factor, maybe we can even write this as a proposition. If you have the square root of, say, x to some even number 2n, this will actually just simplify to x to the n, right? So for instance, the square root of x to the 18th power would be x to the 9th, because 18 over 2 is 9. So that's always going to be true. That's a little proposition. So in this case, we had x to the 8th. We took its square root. So divide the exponent by 2 and you get 4. So that's something useful. So this is x to the 4th times the square root of x. Okay. This one is nothing too complicated. We've just got some fractions going on. So we can just use that property that we talked about before. Square roots play nice with division. So we know this is the square root of 1 over the square root of 9. And the square root of 1 is 1. The square root of 9 is 3. So that's just a third. Okay. Now we get something slightly more complicated, but again, we can still put it together in the same way. Again, notice they're stating that x is greater than 0, so we don't have to worry about any type of absolute value type of deal here. So number 48, if we do the square root of 256x cubed over the square root of 4x, we can make that one big square root and just divide the numbers, right? 256x cubed over 4x. So 256 over 4 should just be 64. So, and x cubed over x is x squared. So we're actually just taking the square root of 64 x squared. And we know the square root of 64 is 8, and the square root of x squared is x. So this is just 8x. That's our final answer here. Okay, and then, so performing this addition for number 49, it's the same as with variables, right? We can treat these radicals as like terms when they follow a regular number. So if you have 6 square root of 3 plus 5 square root of 3, it would be the same as if you were adding 6x plus 5x. You would just add the numbers in front and keep the trailing object the same. So 6 plus 5 would be 11, so this is actually 11 square root 3. And you would be completely simplified at that point. Similar thing here. The square root of 13x makes these like terms, so we just need to do 4 minus 9, which is negative 5. So the square root of 50, you have 4 square root 13x minus 9 square root 13x, and the 4 minus 9 would make negative 5, so this just simplifies to negative 5 square root 13x. This is just like simplifying like terms with regular variables. All right, now in number 51 here, these are not like terms, right? You can't just put them together as is. So we need to try and simplify the radicals. Again, you want to look for things that you know are square roots that are factors. So 75, I know 25 goes into that, and that's going to be a perfect square. And for 27, I know 9 goes into that. So that's going to be a key to simplifying number 51. So number 51, I have this square root of 75x minus the square root of 27x. And I'm going to rewrite this as 25 times 3 times x. And I'm going to rewrite 27x as 9 times 3 times x. So the square root of 25 will simplify to a 5, and the other two, the 3x, will still remain inside the radical. That cannot be simplified any further. And with the second term, the square root of 9 would also become a 3, and the other 3x would remain below the radical as well. That cannot be simplified further. Now we have two terms that are like terms, so we can just do the 5 minus 3, and we are left with 2 square root 3x. And that is it for part A. Okay, similar thing going on here with 52. A lot of practice simplifying these radicals. Although it comes up a bit the rest of the semester, but nowhere near as intensely as this. Again, we're going to use the same trick. 25 goes into 75, and 4 goes into 12. So we've got 6 square root 75 plus 3 square root 12. And 75 I'm going to think of as 25 times 3. And 12 I'm going to think of as 4 times 3, because I know the square root of 25 and I know the square root of 4. So I get 6 times 5. The 3 remains inside the square root. The second term I have 3 times 2, and the 3 remains inside the square root. So 6 times 5 is 30, so I have 30 square root 3 plus 6 square root 3. These are now both like terms, so 30 plus 6 gives me 36 square root 3. Okay, rationalize the denominator. This is a technique where you just don't want any square roots in the denominators. You want them only in the numerator. So it's pretty simple. If you multiply any number with itself, it will then become a perfect square. But what's going on with a fraction is we just have an expression here, so we cannot change its value. So we're only allowed to multiply by something that has a value equivalent to 1. So I would call this a clever form of 1. So what I'm going to do is I'm going to multiply by the square root of 7 divided by the square root of 7, because that's equal to 1, right? But now what happens? I end up with the square root of 5 times 7 on top, which is 35. And on bottom, I would end up with the square root of 7 times 7, or 7 squared. And we know that the square root of anything squared is just that number. So we end up with just 7. So this comes out to the square root of 35 divided by 7. That would be the simple radical form. Okay. When you have something more complicated like number 54 here, we have to use a trick known as multiplying by the conjugate. This will come up later in factoring as well. So the trick multiplying by the conjugate relies on the fact that if you have an a plus b and you multiply it by a minus b, you'll end up with a squared minus b squared. Because what you have to do to multiply those two binomials is you actually have to FOIL them out, right? You have to multiply the first terms, the outside terms, the inside terms, and the last terms. But the outside terms would be minus AB, and the inside terms would be plus AB. So your outside and inside terms cancel. So you end up with just a squared minus b squared. So when we have this expression, 17 divided by 5 plus the square root of 37, we again still need to multiply by something equal to 1, but now we have something more complicated in the denominator. You can't just multiply by the same thing because you would still have radicals left over from the FOILing process. So we need to multiply by the conjugate. So here a is acting like 5 and b is acting like 37, or the square root of 37 rather. So I'm going to multiply by 5 minus the square root of 37 on top and bottom. So that is my clever form of 1 for this problem. So then the top, I just have 17, and I need to distribute that to 5 minus the square root of 37, which I'll take care in a moment. But on the bottom, I will end up with 5 squared minus the square root of 37 squared from multiplying by the conjugate. So then I just end up with, distributing the 17 on top, I'll end up with 85 minus 17 square root 37. And on bottom, I'll have 25 minus 37. So in fact, that will come out to negative 12 in the denominator. So I'm just going to leave the fraction like that. 85 minus 17 square root 37 over negative 12. And it may look a big old mess to you, but the main point is that there are no longer any radicals remaining in the denominator. So if you have two terms in the denominator and one of them is a radical, the only way to eliminate that radical is by multiplying by the conjugate. That may test some of your algebra skills if you have not done it in a while. I would say maybe that's one of the more challenging problems we'll have, but it won't come up so often in the future. The multiplying by the conjugate trick will be used more often for factoring, and it's known as the difference of squares in that context. Okay, so we have another one of these. We'll go through it just for the practice since these are kind of difficult. So we have 7 divided by the square root of 10 minus 3. So we multiply by the conjugate, which is the same thing, that square root of 10, but with a plus. And we do that on top and bottom. So on top, I just kind of leave it alone before distributing. And on bottom, I know it's going to be the square root of 10 squared, which will just come out to 10 minus 3 squared. So this one's quite nice because the bottom is just going to come out to 1. So I have 7 square root 10 plus 21, multiplying the 7 to both terms. And on bottom, I have 10 minus 9, which comes out to 1, which means I just have 7 square root 10 plus 21, and that's it. So I have 7 square root 10 plus 21. Okay, so then we have some other radicals, and when you have other radicals, they're just canceling out with different powers. So the way that square roots canceled out with powers of 2, cube roots, that little 3 there, means it will cancel out with powers of 3. So the main thing to remember if you have something like this is the nth root of x to the n is always just equal to x, right? So we want to look for third powers. So the thing is, the powers as they grow larger, they're a little more difficult to do mentally just because the numbers get big so fast. But if we think about, for this one, we have the cube root of 36 times the cube root of 30. We'd want to ask ourselves, well, is there anything really that would simplify? So, 1 cubed is 1. That doesn't help us for simplification. 2 cubed is 8. 3 cubed is 27, and so on. So we don't see any of those going into each other, but we will see if we have a combination of them. Maybe they will. So if we multiply these things together, the cube root of 36 times 3, that would be 1980, is that right? 1080. So it might not be clear if anything's going into that. You could check on your calculator. Maybe the easiest way is to do a factorization tree. And if we're doing a factorization tree, I don't know. I don't want to do something that's too difficult. I mean, you could check that this number, you could say, okay, is this divisible by 8? And it is. And you can also check if it's divisible by 27. And it is as well. So maybe that's one way to do it. If you check that, what we have here is we actually have 8 times 27 times 5. And we know from up here that we know 2 of those cube roots. The cube root of 8 is 2, and the cube root of 27 is 3. So this would really be 2 times 3 times the cube root of 5. So this actually is 6 cube root of 5. That would be the answer here. I'll show you also how to break this down into a factorization tree, because maybe that's difficult for you to see that those numbers go in. I just have intuition because they're small numbers and there's not going to be that many options. Let me just show you how a factorization tree would work. If you have this number 1080, you could break it down by dividing it by things that are obvious. So you could say, okay, well, this is even, so I know 2 goes into it, and you end up with 540. And then you could say, well, I know 2 goes into that, and then say, okay, well, that has to be 270. And then say, okay, 2 goes into that, and I have 135 left over. And then you could say, okay, well, I know that's divisible by 5 because it ends in 5. And then that would be 27. And then I know 27 is 3 times 9, which is 3 times 3. Now, the end of all of these branches is going to be a number in the prime factorization. So essentially, the prime factorization of 1080 is there's 3 copies of 2, 3 copies of 3, and 5. So that would be the prime factorization of 1080, and that's why we can break it down into the 8 times the 27 times the 5. So this is the known as the prime factorization, and this is a factorization tree, which is how you can do it step by step. So that's also a method for finding the cube root there. Okay, let's go ahead and do number 57. So for number 57, we have the cube root of 256 x to the 4th over the cube root of 4x. And just like with radicals, we can combine these into a single cube root, because all of these radicals really denote exponents, and those are going to do well with multiplication and division. So we know that 256 over 4 is 64. So we have the cube root of 64, and then x to the 4th over x. 4 minus 1 would make that x cubed. So, yeah, it turns out that if you would go one more in the list of cubes that we had before, 4 to the 3rd power is actually, so I'll write that down after the fact, but 4 to the 3rd power is 64. 4 times 4 is 16, times 4 is 64. So this actually just comes out exactly to 4x. And we could say that's because, at least for the 64, 4 to the 3rd power is 64. So, yeah. Okay, then we have, again, some ones that we'd like to combine with these cube roots. Again, we're going to be looking for those numbers on our list so far. They get big quite rapidly, but the ones we've seen so far are 2 cubed is 8, 3 cubed is 27, and 4 cubed is 64. So are any of these numbers divisible by those? And upon a little inspection, 81 is just 27 times 3, and 192 is really just 64 times 3. So that's going to make life easier when we're trying to simplify these. So we have 6 cube root 81 plus 3 cube root 192. So check those numbers that we've seen so far. So we have 6 cube root, what did we say? We know this is 27 times 3, and we know that 192 is 64 times 3. And the cube root of 27 is just regular old 3, so we end up with a 6 times 3, and then there's 1 3 left over inside the cube root, and then 64, the cube root of 64 is 4, so we just have 4, and then 1 cube root of 3 left on the inside. So we have 18 cube root of 3 plus 4 cube root of 3, which leaves us with 22 cube root 3. And that would be our final answer. Okay, one other thing for notation purposes. Again, all of these radicals can actually be written in exponent notation. So we have some notation. How can we convert back and forth? Well, if you have the square root of some number x, this is the same thing as x to the 1/2 power. And if you have any other root, say the nth root of x, as an exponent, this is written as 1 over n. Okay, so if you have the cube root of a number, say we're taking the cube root of x, that would be the same as x to the 1/3 power. So here we've got 121 to the 1/2. Well, we know that's just the same as the square root of 121. And the square root of 121 we saw was 11. Oh, they say do not evaluate, so that means we have to start by leaving it as a square root, and then maybe they'll ask us to evaluate. What? Oh, I wrote 11, not 121. Okay, now evaluate, so we know that's 11. Okay, when you have multiple powers, the top power goes with the x, and the bottom number is always the root. That's the easiest way to think of it. So if we have 243 to the 3 over 5, the 3 would be the power, and the 5 would be the root. So this would be the same thing as the 5th root of 243, I wrote 233, 243 to the 3rd power. So that's how they want us to start. So we start with this 5th root of 243, and then we need to raise the whole thing to the power of 3. Okay, then they want us to evaluate. Well, the 5th root of 243, that's 3 to the 5th power makes 243, right? 3 cubed is 27, to the 4th is 81, and to the 5th is 243. So we end up with 3 to the 3rd power, which is 27. So our answer here is 27. Usually on a calculator, you can just raise it to an exponent and then type that fraction in. So let me see if I can do it on the Windows calculator. It's not the best calculator in the world, but we'll see. So let's say I were trying to do this. I could say, okay, well, I have 243, and then x to the y means power. And then I would have to do the power in parentheses so that it gets the whole fraction. So 3 over 5, then close the fraction. And I get 0.6. What? Oh, no. There we get 27. I had to hit equals. So there we go. 3 over 5 is 0.6. So the exponent is 0.6. And then 243 to the 3 over 5 gives 27, as we saw. So you can do it on the calculator. Again, visually, the Windows calculator is not the best. Probably on Desmos, you have a better chance of seeing the actual like math type. I don't know if that's a... So I like to use this Desmos site. Math tools. Let's see their scientific calculator, see if it's better. Probably 243 to the... See, it makes the actual exponent for us, so I don't need the parentheses here. So the Desmos calculator is a bit better because visually it'll write it in the math notation you're accustomed to writing by hand. So anyhow, last few questions to look at. Number 61, we have 64 to the negative 5 over 6. So remember, the negative really just means it's 1 over that value. So we can actually write this as 1 over 64 to the 5 over 6. And then we would be doing the each one, but remember 1 to any power is always going to be 1, so I can actually just write this as 1 over the 6th root of 64 to the 5th power. Remember, the bottom number is the root and the outside number is the power. Let's see if they accept it like this. Sometimes it's hard to tell. 6th root of 64 to the... Oh, gotta get outside the radical. To the 5th. Yeah, so they accept it like that. The 6th root of 64 is just 2, so we end up getting 1 over 2 to the 5th, and 2 to the 5th is 32, so we get 1 over 32 as the final answer. Again, you can appeal to the calculator if your mental math is not quite as sharp. Okay, properties of exponents. The regular numbers we can just multiply, and then the exponents we're going to want to add. So 4x to the 1/2 times 3x to the 1/5. Okay, 3 times 4 we can certainly do. That's just 12. And then the x's we want to add the exponents. So we have 1/2 plus 1/5. Remember, to add an exponent, we need to get a common denominator. So a common denominator would be 10. So maybe we'll do that just over here on the side. 1/2 plus 1/5. Well, 1/2 is 5 over 10. And 1/5 is 2 over 10. So this would come out to 7 over 10. So this is really 12x to the 7 over 10. And they want us to use fractional exponents, so that would be the final answer. 12x to the 7 over 10. So the way that we said square roots divide the exponent by 2, same thing with cube roots, except for they will divide it by 3, right? So if we have the cube root of x to the 6th, we know 6 divided by 3 is 2, so this will just come out as x squared. So that one's actually pretty simple. And same thing here. Remember, the power goes on top and the root goes on the bottom of the fraction. So it's quite simple to rewrite this. Yeah, maybe I could add that step too if you want to see that step for the previous one. It's the same as x to the 6 over 3, which comes out as x squared. So for this one, the 15th root of x to the 6th, this would be power goes on top, root goes on bottom. Both of those are divisible by 3, so this would simplify to x to the 2 over 5. And that would be it. Did I do something wrong? 2 over 5. Oh, they want us to use radicals? Simplify using radicals. Okay, so we can rewrite that just as the 5th root of x squared like this. So you got to watch those instructions. They like to switch things up quite frequently. So let's do the 5th root of x squared. Okay, all set. Okay, so that's it for the first module homework. If you have any other questions, just send me an email. Otherwise, this is Dr. Lennon signing out.